Hi, this is a lecture introducing the quantum mechanics problem called the particle in a box, or the particle confined to the infinite potential. Um, yeah, so this lecture video is meant to be an introduction to tell you about why we might study such, honestly, an unrealistic model. Um, but here is kind of the setup. So we're modeling a particle in a box. We're going to say that we definitely know that the particle has mass m. And, sorry, let me choose a color. So we definitely are saying, I want to model a particle of a certain mass. So typically these problems model particles that are really, really small. So like you might say a neutron or an electron or a proton or even an alpha particle, which is a helium nucleus, or even maybe an entire atom, right? I don't know if you want to model a DNA molecule this way, but you might model one of the electrons on a DNA model, on a DNA molecule. So a single electron confined to a DNA molecule might be a reasonable use of this particle in a box model. But let me go on to say that this is strictly a model of a single particle. So we're picking only this object of mass m as the subject of our model. So what we're going to go on to say is we have reason to believe that the thing that we want to model is the situation of a particle that is stuck inside of an interval, right? So we're in the explorations after this lecture, we're going to say that along the x-axis, our particle is going to be stuck between x equals to 0 and x equals to L. So the interval is just of length L. And we're going to choose to coordinatize the interval from 0 to L. But yeah, so somehow our particle is stuck inside. And that's what we know. So that's what we're going to model. But furthermore, for this particular example of a quantum mechanics problem, I think this is kind of important to point out. So we have a physical situation where we know a particle is stuck in this interval, and also we don't really have any reason to suspect that in the interval that there is any special places, right? So if the particle was here, the particle is going to be treated the same by its environment as if it was here instead or there. I'm going to show you what that means in terms of Schrödinger's equation in just a second. But what we'll also say is that part of this sort of physical situation is that there are boundaries. And the boundaries will always reflect the particle. If it seems like it's on the way out of the interval, it will always be caused to be kicked back into the interval, right? So somehow there's a physical scenario where the particle is actually free inside the interval and not free only at the boundaries. And both boundaries are the same. That is, it's sort of left and right side symmetric. Yeah. So if you suspect that you're studying a system that fits these following 4 sort of descriptive points, then you might be able to get a lot of predictive power and exploration power in modeling your physical system as a particle in a box. So what I'm going to describe next is how do we impose these stipulations for a quantum mechanics problem, right? How do we give ourselves this quantum mechanics problem? Well, quantum mechanics starts with Schrodinger, right? Or the Schrodinger equation. And the Schrodinger equation, we're going to do this. So the interval properties are independent of time. That is, the interval L is not changing in time, and the fact that the boundaries will strictly only bounce your particle back into the interior, that's also not time dependent. It's not like the sense of the interval turns on and off periodically or any sort of time dependence, right? It doesn't get weaker, it doesn't get stronger, it's just always the same. So if the interval properties are independent of time, and we need to use a Schrodinger equation, we can at least start off our problem with a time-independent Schrodinger equation, right? And the time-independent Schrodinger equation looks like this. For a single particle, the mass shows up in the first term, which is the double space derivative. Oops. We're thinking of this problem as a one-dimensional problem because we're saying that the particle is only confined to this interval, say in the x direction, whereas in the y and the z, honestly, it's just simply not described. So we have reasons to study this problem as a one-dimensional problem. So here is the time-independent Schrodinger equation. So we add on a potential energy function, u of x, multiplying the wave function psi of x. And for the case of the time-independent Schrodinger equation, this is equal to the energy multiplied by psi of x. And I'd like to point out something, that the energy is always independent of space. So you will never see E of x. The energy is strictly independent of space. It is a number. What's more, if it's really meant to mean energy, then it has to be real. And it has to have units, for example, of joules or electron volts or something like that, right? So, but E is always just going to be a number, and it should always be real. Same as for U is meant to be a potential energy. It should be real for sure. It can be negative or positive, but the potential energy is actually a function of space in general. Since we're only studying the time-independent situation, which we have reasons to do so because of what we think we need to model, right? The potential energy function is independent of time. Okay, so u of x, as you might suspect, has something to do with our interval, right? From 0 to L, our interval and boundaries. And so the particular situation of u of x is u of x needs to do whatever it needs to do in order to guarantee that our particle is inside the interval and cannot exist out of it, right? So we need to choose a u of x that's going to do this, number 3, and then we also must have a u of x that does number 4, the sense in which no place is special except the endpoints, the boundaries, 0 and L. And the potential that guarantees numbers 3 and 4 up here, the only potential that does that is this one, and I'm going to define it in piecewise and then draw a picture. So we'll say that the potential energy of our particle is infinity if x is less than 0. So positions on this interval here, from 0 to L, the particle's allowed to be in there. But for negative values of x, so x less than 0, we don't want the particle to have any possible existence outside of that. So the way we make it impossible is we say that the only way that you're allowed to exist in positions less than 0 is to have an energy that's bigger than infinity. So that's an impossibility. We'll do the same kind of restriction, that the particle must have at least an infinite amount of energy to exist beyond the positive side of the interval. And we'll say that in between the interval's bounds, the requirement of energy is uniformly the same value. It's uniformly 0. Yeah. So what's interesting about this is if you study what about the force in the x direction, if you remember, it's related to the potential, which is the derivative in the direction in which you want to know the force. So it's du by dx if I want to know the force in the x direction, but there's a minus sign. So if I look at the potential energy transition between x being negative into x becoming 0, right, that potential is, it starts off at infinity and all of a sudden drops down. And the slope of a function like this, right, if you look at, so this is x equals to 0, so u drops precipitously, right? So the slope of this, right, is rise over run. So it rises a negative infinity amount divided by 0. So the slope is negative infinity. And the negative sign on negative infinity is that the force is positive infinity, right? So at x equals to 0, the force equals positive infinity. That's the force in the x direction. What this force does is immediately turns your particle around and pushes on it in the positive x direction. But if you look at the transition at x equals to L, it's the opposite direction, right? So the potential is 0 until x equals to L, at which position the potential goes to infinity. And this slope is positive. It's actually positive infinity. So that means that the force, which always has the minus sign on the slope, is in the negative direction. It pushes the particle back into the interval. And because the slopes are infinite in strength, what that means is that no matter what the particle is doing, it's going to be kicked back into the interval. All right? Okay, so yeah, these are these things. So we are set up with a problem that we're going to solve in the next video. The problem that we're going to solve is Schrödinger's equation with this potential right here. It's piecewise defined, and you might consider it a toy model that can be useful to study, essentially approximate the quantum mechanics of simple situations involving a single particle.